You see that headline? Interstellar visitor grows tail pointing at the sun. Every rule of comet's broken. Scientists baffled. Except they are not baffled at all, and nothing is broken. July 1st, 2025. Atlas station in Chile catches something moving fast, really fast. 61 kilometers per second. That is twice the escape velocity. Hyperbolic trajectory confirmed within 72 hours. Third interstellar object ever detected. The internet goes wild. But here's what most outlets will not tell you. 3 separate misconceptions about this comet's tail spread faster than the comet itself. And every single one of them is wrong in a fascinating way. A normal antisolar tail pointing away from the sun, a sun-facing dust plume from its heated hemisphere, and depending on Earth's viewing angle, an apparent anti-tail from perspective effects. 3 different things. The media blurs them together. Headlines scream anomaly. One researcher calculates a 4 out of 10 on his self-invented alien technology scale. Meanwhile, comet scientists point to a 1974 paper by Zdenek Sekanina titled On the Nature of the Anti-Tail of Comet Kohoutek. They point to observations of Comet Arend Roland from 1957. They point to Comet C 2014, UN 271 Bernardinelli Bernstein, showing the exact same sun-facing dust emission in 2021. Not new, not unique, just rare and fascinating. The discovery itself deserves attention. ATLAS, Asteroid Terrestrial Impact Last Alert System, operates multiple telescopes. The Chilean station in Rio Hurtado caught the object first on July 1st, 2025. Within 48 hours, Deep Random Survey in Chile, Lowell Discovery Telescope in Arizona, and Canada-France-Hawaii Telescope at Mauna Kea all confirmed it. All detected a marginal coma with potential tail-like elongation spanning 3 arcseconds. Comet confirmed. On July 2nd, the Minor Planet Center announced the discovery and assigned the interstellar designation 3I. By the time the official name came through, the MPC had collected 122 observations from 31 different observatories. Orbital eccentricity measures whether an object is bound to the sun. Ellipse has eccentricity between 0 and 1. Parabola hits exactly 1. Hyperbola exceeds 1. 3. I-Atlas clocked in at eccentricity 6.1, not barely escaping, blasting through at massive excess speed. That number alone proved interstellar origin. This script is researched and factual, using sources from the Planetary Society's August 2025 interview with Dr. Bryce Bolin, published in their Planetary Radio series, where Bolin discusses observing all 3 known interstellar objects, and from peer-reviewed Hubble Space. Telescope observations led by David Jewett at UCLA published through NASA's Scientific Data Archives in August 2025, documenting the actual measured dust ejection rates and coma morphology. These are not blog posts. These are observation logs with instrument specifications and error bars. Now back to the information. This one spreads because it sounds technical. It uses the phrase radiation pressure. It invokes solar wind. Problem is, it confuses 3 completely separate phenomena, and it ignores what actually happens to dust particles of different sizes. Hubble Space. Telescope images from July 21st, 2025, show 3 I-Atlas at 277 million miles from Earth. The comet displays a teardrop-shaped cocoon of dust. Enhanced image processing reveals 2 distinct features. 1, a faint broad tail pointing eastward away from the sun. 2, a dust plume extending westward toward the sun. The anti-solar tail spans roughly 56,000 kilometers by late August, confirmed by Gemini South telescope observations on August 27th. The sun-facing plume appears in the inner coma within 5 arcseconds of the nucleus. Both exist simultaneously. Both are real. Neither violates physics. That creates the normal tail. Large dust grains, 100 micrometers radius, get ejected at only 2 meters per second, too heavy for radiation pressure to overcome their momentum. They drift in the comet's orbital plane. From these measurements in July, Jewett's team calculated the comet was releasing 6 kilograms of small dust per second and 60 kilograms of large dust per second, 10 times more mass in the heavy particles. The heavy stuff does not get swept back. It accumulates along the orbit. Think about the physics for a moment. Radiation pressure depends on surface area. Mass depends on volume. A particle twice as big has 4 times the surface area but 8 times the mass. The ratio flips against radiation pressure as particles grow. A 1 micron grain might experience radiation pressure forces 2.5 times stronger than solar gravity. That ratio is called beta. Beta greater than 1 means the particle escapes. Beta around 0.5 means radiation pressure dominates, but the particle stays in a highly elliptical orbit. Beta, near 0.1, means gravity wins, and radiation pressure just nudges the trajectory slightly. They blow out fast. Medium grains at 50 micrometers sit around beta 0.5. They form the curved dust tail visible in most images. Large grains at 100 micrometers or bigger drop to beta below 0.2. These particles are essentially on ballistic trajectories. When you eject a ballistic particle from the sun-facing side of a rotating nucleus, it goes in whatever direction the ejection velocity plus the nucleus rotation velocity points. Some of that is toward the sun. The particle then falls into an orbit around the sun that is nearly identical to the comet's orbit, just slightly offset. They form a torus, a donut shape, centered on the comet's orbit. When Earth passes through the plane of that torus, we see it edge on. All those millions of particles spread over vast distances compress into a line in our view. That line points both toward and away from the sun depending on which side of the nucleus you measure from. Media reports focus on the sun-facing side and call it an anomaly, but it is geometry, not physics violation. Comets sublimate ice preferentially on their sun-facing hemisphere. That is where the heat is. That is where the pressure builds. That is where gas jets accelerate dust fastest. The James Clerk Maxwell Telescope measured hydrogen cyanide production on September 7, 2025, at 1.5 times 10 to the 25th molecules per second, when 3I Atlas sat at 2.33 astronomical units from the sun. 1 week later, September 14th, the rate tripled to 4.5 times 10 to the 25th molecules per second. 2 kilograms per second of cyanide gas rushing outward. That gas drags dust with it. The sun-facing side is hotter, more active, ejects more material, simple thermodynamics. Michael Bush at UCLA explains it plainly on social media in August 2025. With a rotating comet nucleus, ejecta from any spot can launch with velocity that puts particles either in front of or behind the nucleus. Does not matter which side it starts from. Small dust and ejected gas get pushed out by radiation pressure and solar wind, but larger pieces of ejecta spread out along the orbit, both in front of and behind the nucleus. Not controversial. Standard dust dynamics. Farnham and colleagues documented this exact mechanism in 2021 studying Comet C, 2014, U-Ian 271. The comet, sitting beyond 20 astronomical units, displayed a sun-facing dust enhancement. Their interpretation, slow ejection of relatively large dust particles predominantly from the sunlit hemisphere, published in peer-reviewed literature 4 years before 3I Atlas. When Dr. Jewett's team saw the same feature on 3I Atlas in July 2025, they cited Farnham immediately. The morphology matches, the physics matches, the particle size distribution matches. The sun-facing plume appears in every observation. The comet's orientation does not change it. Earth's position does not change it. The plume always points at the energy source, the sun. By late August, the anti-solar tail has grown visible enough that both features appear in the same frame. Sun-facing plume to the right, anti-solar tail to the left, one comet, 2 emission mechanisms, 0 violations of physics. The feature spanned 12 degrees across the sky. Disappeared by April 29th, Sylvain Arendt and Georges Roland discovered it. November 8th, 1956. By April 20th, it shone at magnitude 0 or 1 with a 25 to 30 degree dust tail. Then, on April 22nd, a second feature appeared, a narrow spike extending toward the sun. It narrowed each day until April 25th, when it stretched 15 degrees like a needle. Scientists calculated the spike required particles between 0.1 and 1 millimeter ejected between February 6th and March 1st, 6 weeks before perihelion. These particles spread into a disk. Earth crossed that disk plane between April 20th and 30th, creating the spike illusion through edge-on viewing geometry. Sekanina analyzed 14 nights of photometric observations from European Southern Observatory. He found the anti-tail required substantial excess of heavy particles, 0.1 to 1 millimeter size, and that dust production was 1 order of magnitude higher than from Arendt-Roland. His paper introduced mathematical formalism still used today, syndynes and synchrones for decomposing anti-tail brightness into size distributions and ejection histories. The paper is 51 years old. It is cited in every major comet tail textbook. Anyone claiming anti-tails are unexplained simply has not read the literature. A plume formed by asymmetric ejection points at the heat source. A debris disk seen edge-on appears as a spike. 3 mechanisms, all well documented. Comet Kohoutek, 1973. Comet Hale-Bopp, 1997. Comet C, 1999. H1 Lee. Comet Lulin, 2009. Comet C 2022, E3 ZTF in 2023. Comet 12P Ponce Brooks, 2024. Comet C 2023, A3 Tsuchinshan Atlas 2024. The list goes on. 3. I-Atlas joins a long roster of comets showing anti-tails or sun-facing dust features. Not anomalous? Rare, yes. Anomalous, no. The argument runs like this. Dr. Avi Loeb, director of Harvard's Black Hole Initiative, observes 3I Atlas with the Keck 2 telescope in Hawaii in August 2025. When the comet sits at 3.8 astronomical units, the spectrum shows cyanide and nickel emission. Loeb's team publishes a preprint on Archive, not yet peer-reviewed, noting evidence for a puzzling anti-tail extension in the direction of the sun. In a September blog post, Loeb asks 2 questions. What is the nature of the anti-tail? Why are comet experts ignoring this anomaly while insisting 3I Atlas is a familiar comet? He ranks the object 4 out of 10 on his personal Loeb scale, measuring likelihood of extraterrestrial technology. He uses an analogy. Imagine noticing a new animal in your backyard with a tail coming out of its forehead instead of its rear end. Experts argue it must be a cat because cats have a tail. You point out cats do not have anti-tails, but experts dismiss the anomaly. Except the analogy fails because comet experts are not dismissing anything, they are explaining it. Jason Wright at Penn State responds directly in late September 2025 on his academic blog. He points out that the paper Loeb co-authored with Eric Kito explains the feature using ordinary comet physics, large dust grains ejected from the sunlit hemisphere. Wright cites the Farnham 2021 paper on Bernardinelli Bernstein showing identical morphology. He notes that Sekanina described anti-tail physics in 1974, not recently. 51 years of established science. Sekanina, 1974 on Kohoutek. Vincent and Probstein, 1968 on Arend Roland. Studies on Hale-Bopp, studies on ZTF, studies on Tsuchinshan Atlas. The phenomenon appears in textbooks. The IAU has formal definitions distinguishing between radiation pressure tails and prospective anti-tails. This is not hidden knowledge, it is undergraduate astronomy. When 3. I-Atlas was first detected in July 2025, some early reports suggested no visible coma, implying a large, inert object. Loeb seized on this, calculating that a non-cometary object of the observed brightness would need to be enormous, tens of kilometers across, anomaly declared. Then Hubble confirmed the coma on July 21st. Object is active. It is a comet. Loeb pivoted. He proposed the coma was a collision avoidance system for a spacecraft. That idea lasted days. He then suggested the coma resulted from interstellar dust accumulated during billions of years of travel, also dropped. Next came claims that most of the brightness was artificial lighting on the craft itself, also abandoned. Then he and Kito published size estimates suggesting the nucleus might be 46 kilometers across, vastly larger than HST observations indicated. Casey Lisa, first author on one-sided paper, publicly stated Loeb misrepresented his work. That paper explicitly gave an upper limit around 5 kilometers, not 46. Meanwhile, Tom Statler, NASA's lead scientist for solar system small bodies, states in October 2025 to The Guardian, it has some interesting properties that are a little bit different from our solar system comets, but it behaves like a comet. And so the evidence is overwhelmingly pointing to this object being a natural body. It is a comet. Nickel has been detected in cometary comae before. The mechanism likely involves parent molecules, possibly polycyclic, aromatic hydrocarbons, that release nickel atoms when broken down by solar ultraviolet radiation. The concentration gradient suggests the parent molecule has a short lifetime. This is interesting chemistry. It might tell us something about the comet's formation environment. It does not require non-natural origins. Drifted through interstellar space for billions of years. The comet's trajectory traces back toward the galactic center direction in Sagittarius. Perez Couto and team at University of A Coruña traced the path back 10 million years in a September 2025 preprint. They conclude it likely originated from the Milky Way's thin disk, a region of younger stars and active planetary system formation. Age estimates vary. Matthew Hopkins at Oxford suggests 3I Atlas could be 7 to 14 billion years old, older than our solar system. That comes from dynamics and orbit analysis, though with large uncertainties. It equals a data point, a chance to study planetary formation conditions in a different stellar environment. The Vera C. Rubin Observatory comes online soon. Projections suggest it might detect multiple interstellar objects per year. If every unusual feature prompts speculation about spacecraft, we will drown in noise. The explanation is unified and consistent. The confusion comes from conflating different features and misunderstanding the observational geometry. 3. I-Atlas has a nucleus, somewhere between 440 meters and 5.6 kilometers in diameter, based on Hubble observations, through August 20th, 2025. Large uncertainty because the nucleus is surrounded by reflective dust, making brightness estimates tricky. The nucleus rotates. Light curve analysis suggests a rotation period exceeding 16 hours. As it rotates, different surface features enter and exit sunlight. James Webb Space Telescope observations through August and September detect all of these. Carbon dioxide dominates, 130 kilograms per second. Water is much lower, 6.6 kilograms per second, only 5% of the CO2 rate. This is unusual compared to solar system comets, where water typically dominates, but not impossible. Just reflects different formation conditions, probably colder, more carbon-rich environment. Small grains, 1 micron radius, ejected at 22 meters per second. Large grains, 100 microns radius, ejected at 2 meters per second. The small grains get blown back by radiation pressure. Radiation pressure acts on cross-section, but not on mass. Small grains have high surface-to-mass ratio. A 1 micron grain might experience twice the radiation pressure force compared to solar gravity. It accelerates outward, anti-solar direction, creating the classic tail. This tail on 3. IATLAS measures roughly 100,000 kilometers by mid-September. Webb's infrared spectrometers detected carbon dioxide as the dominant volatile, 130 kilograms per second production rate. Water vapor, much lower, 6.6 kilograms per second. Carbon monoxide intermediate at 14 kilograms per second. This ratio is backwards from typical solar system comets. Comet Halley produces about 80% water by mass. Comet Hale-Bopp also water-dominated. Even 2 I-Borisov, the previous interstellar comet, showed water as the primary volatile. 3I Atlas flips the script. Carbon dioxide dominates by a factor of 20 over water. Carbon dioxide ice sublimates around 60 to 80 Kelvin. Carbon monoxide even colder, 25 to 30 Kelvin. A comet forming in a cold outer disk region far from its star would retain more of the supervolatiles, like CO2 and CO. Water would be present, but not dominant. 3. IATLAS probably formed in a planetary system's outer reaches, maybe an analog to our Kuiper belt or Oort cloud, maybe even farther out if its home star was dim. The chemical fingerprint suggests a cold nursery. Only a handful of detections. OCS forms from sulfur-bearing ices mixed with carbon and oxygen. It requires specific chemistry. Detection suggests 3. IATLAS contains sulfur-rich material, possibly inherited from its parent molecular cloud. The sulfur might be bound in complex organic molecules. When solar ultraviolet radiation breaks these molecules apart, it releases simple species, like OCS. The presence of sulfur compounds hints at primitive, unprocessed material. This comet might preserve chemistry from the earliest days of its birth star system. Hydrogen cyanide, HCN, is common in comets. It produces strong emission bands in visible and millimeter wavelengths, but the production rate matters. James Clerk Maxwell Telescope on Mauna Kea measured HCN on September 7th and 14th, 2025. The production ramped up from 1.5 times 10 to the 25th molecules per second to 4.5 times 10 to the 25th molecules per second in 1 week, tripling in 7 days. That implies either increasing solar heating as the comet approached perihelion, or a rotating nucleus exposing different terrain with different volatile content, or an outburst event where fresh ice got exposed suddenly. The cyanide coma on September 15th measured 180,000 kilometers across, larger than Jupiter. Asymmetric too, elongated along the anti-solar direction, gas being blown away by solar wind while still glowing from fluorescence. Keck Observatory spectra from August 2025 detected neutral nickel atoms in the coma, not ionized, neutral. Nickel atoms absorb and emit specific wavelengths in the green part of the spectrum. The emission was concentrated. Most of the nickel flux came from the innermost 2,000 kilometers of the coma. Beyond that, nickel signal dropped fast. What releases nickel? At 3.8 astronomical units from the sun, temperatures are too cold to vaporize metallic nickel directly. Nickel metal sublimates above 1,000 Kelvin. 3. IATLAS surface temperature maxes out around 200 Kelvin at that distance. The nickel has to come from a parent molecule that breaks down quickly in sunlight. This is the compound used in industrial nickel refining. It forms when nickel metal reacts with carbon monoxide under specific conditions. It is volatile, boils at 316 Kelvin. It photodissociates rapidly in ultraviolet light. Lifetime in sunlight measured in minutes. If 3. IATLAS contains grains of metallic nickel coated in or mixed with carbon monoxide ice, and if those grains get exposed to moderate temperatures and low pressures in the coma, nickel tetracarbonyl could form transiently and then break apart, releasing nickel atoms close to the nucleus. The concentration gradient fits this model, nickel atoms produced within 2,000 kilometers, then dispersing into the larger coma and getting lost against the background. The detection is real. The mechanism is speculative but plausible. The compound itself is not unknown. It exists on Earth, produced industrially. Finding it naturally in a comet would be novel but not impossible. A 100 micron grain is 1 million times more massive than a 1 micron grain, but only 10,000 times larger in cross-section. Surface to mass ratio drops, radiation pressure, force drops. The particle is effectively ballistic. It leaves the nucleus with the velocity imparted by gas drag and then coasts. If ejected from the sun-facing hemisphere, it initially moves toward the sun. Then solar gravity bends its trajectory into an orbit similar to the comet's. These particles accumulate in a disk along the orbital path. When Earth crosses the comet's orbital plane, we see that disk edge on. The entire disk of large particles spread out over millions of kilometers projects into a narrow spike in our view. The spike appears to point at the sun, not because particles are moving toward the sun, but because we are viewing a three-dimensional distribution edge on. Stand at the galactic disk and the Milky Way appears as a band. Same principle. The anti-tail is not tail material moving sunward. It is orbital debris viewed from an angle that makes it look sunward. The subsolar point on the nucleus receives maximum heating. Sublimation rates peak there. Gas pressure peaks there. Dust gets launched faster. The result? An asymmetric coma elongated toward the sun. Very large telescope images from late August show this clearly. The inner coma, within 5 arc seconds, appears fan-shaped and brighter on the sun-facing side. This is the plume. Not a tail, not orbiting debris, active emission. Debris disks along the orbit, formed by large grains too heavy for radiation pressure, appearing as an anti-tail spike when viewed edge-on. Sun-facing plume in the inner coma, formed by preferential sublimation on the heated hemisphere. All three have been observed in other comets. All three occur simultaneously on 3I Atlas. The explanation is not competing theories. It is one unified model accounting for different observational features at different scales. Also comment what city you're watching from. This analysis draws from Dr. Jason Wright's September 29th, 2025 academic blog post titled 3I Atlas's Anti-Tail Isn't Unique, where Wright provides detailed citations to historical anti-tail papers, including Sekanina's 1974 work and Farnham's 2021 study of Bernardinelli-Bernstein, demonstrating that the phenomenon has been understood for over 50 years through peer-reviewed research published in Icarus and other astrophysics journals. We also reference the October 2025 article in The Guardian quoting NASA scientist Tom Statler, confirming the consensus that 3I Atlas behaves as a natural comet. Now back to the information. Tail can mean the radiation pressure tail, the debris trail, the anti-tail spike, or the sun-facing plume, depending on who is writing. Media outlets do not distinguish. Part of it is the alien angle. Interstellar equals mysterious. Mysterious equals potentially artificial. That leap requires ignoring Occam's razor, but it generates clicks. Early estimates of the nucleus size span 2 orders of magnitude, from hundreds of meters to tens of kilometers. Hubble narrowed it down, but still leaves factor of 10 uncertainty. Is it 440 meters or 5.6 kilometers? Both fit the data, depending on how much dust contamination you assume. Uncertainty invites speculation. The rotation period is long, but not precisely determined. The trajectory aligned close to the ecliptic plane is statistically unlikely. Most interstellar objects should come from random directions. None of these features require non-natural explanations, but they all merit follow-up study. Problem is, 3. I-Atlas is leaving. Perihelion, October 29th, 2025. At 1.4 astronomical units inside Mars' orbit. Then it swings past Jupiter in March 2026 and exits the solar system forever. The observation window is closing. Multiple spacecraft tried to catch glimpses. ExoMars. Trace Gas Orbiter imaged it October 3rd from Mars. Europa Clipper was potentially immersed in the ion tail between October 30th and November 6th. JUICE might observe it in late October or early November. SphereX observed it August 7th through 15th. James Webb took spectra. Hubble tracked it for months. Parker Solar Probe, SOHO, Mars Reconnaissance Orbiter, Curiosity, Perseverance, all turned instruments toward it when geometry allowed. We are throwing everything at this object. Even with all that firepower, some questions will remain unanswered when it leaves. Its camera, CASIS, the color and stereo surface imaging system, is designed for close-up terrain mapping, not distant comet chasing. But on October 3rd, when 3I Atlas passed within about 50 million kilometers of Mars, the team reprogrammed the instrument. CASIS took 5-second exposures. Long for a surface imager. The comet appeared as a fuzzy white dot moving against background stars. Magnitude around 14th or 15th, 50,000 times fainter than what the camera usually observes. Yet the coma resolved. Visible structure, gas and dust clouds surrounding the nucleus. The images confirmed the comet remained active at 1.6 astronomical units from the Sun, closer to perihelion and heating up. The observation proved interplanetary coordination works. Spacecraft at Mars can contribute to targets of opportunity if the timing aligns. Europa Clipper is on its way to Jupiter, launched October 2024, arrives April 2030. En route, it flies through the solar system on a complex trajectory using gravitational assists. Late October 2025, Clipper crossed paths with 3 Arcari Atlas's ion tail. Not a physical collision. The ion tail is diffuse plasma stretched over millions of kilometers. But Clipper carries a magnetometer and plasma instruments. If the spacecraft passed through regions where the solar wind interacted with 3 I-Atlas's outgassing, those instruments could detect magnetic field draping, pickup ions, changes in plasma density and temperature. The observation window ran October 30th through November 6th. Data retrieval takes time, analysis takes longer. Results may not come for months, but if successful, it would mark the first time a spacecraft sampled an interstellar comet's ion tail in situ. We have sampled solar system comet tails before, Ulysses through Comet McNaught in 2007, Giotto through Halley in 1986, never an interstellar one. Also on a complex cruise trajectory, its path brought it into potential viewing geometry of 3I Atlas around late October, early November 2025. JUICE carries cameras, spectrometers, particle detectors. Any observations would complement the Europa Clipper data. 2 spacecraft, different positions, different instruments, targeting the same comet within days. Coordinate that across interplanetary distances, and you start building 3-dimensional maps of the coma structure, tail geometry, gas production variations. Even if the data is sparse, it adds to the inventory. Its job is to map the entire sky in infrared wavelengths, searching for water ice signatures in stellar nurseries and galaxies. Not designed for comets. But 3I Atlas appeared in its field of view during August. SphereX captured spectral data from the comet over 8 days, August 7th through 15th. The team analyzed brightness and concluded that if 3I Atlas were a solid body with no coma, its diameter might reach 46 kilometers based on reflected light at 1 micrometer wavelength. This number got weaponized in the artificial origin debate. 46 kilometers is huge for a comet. That is bigger than Hale-Bopp, way bigger than most known comet nuclei. Problem is, the calculation assumes no coma. Hubble already confirmed the coma existed. The SphereX number is an upper limit for a non-outgassing object. It does not apply to an active comet surrounded by reflective dust. Misinterpretation, not anomaly. First light expected in late 2025 or early 2026. The Rubin Observatory uses an 8.4 meter mirror with a 3.5 degree field of view, enormous by telescope standards. It will photograph the entire southern sky every 3 nights down to magnitude 24. That is 4 magnitudes deeper than current wide field surveys. Deeper means seeing fainter objects. Fainter means more distant or smaller objects become detectable. Simulations predict Rubin might find 1 interstellar object per year, maybe more. Some estimates go as high as 1 per month during peak survey efficiency. If those predictions hold, 3. I-Atlas will be the last rare interstellar visitor. Starting 2026, they become routine. We will build statistics. We will compare compositions, orbits, activity levels, nucleus sizes. We will learn which features are typical and which are outliers. Maybe 3. I-Atlas's carbon dioxide dominance is common among comets from metal-rich stellar environments. Maybe the nickel emission shows up in 10% of interstellar comets. Or maybe 3. I-Atlas is genuinely unusual even among interstellar objects. We need sample size to know. Dust and gas emission confirmed, chemical composition measured. We know it has a normal antisolar tail formed by radiation pressure on small dust grains. We know it has large dust grains, preferentially ejected from its sun-facing hemisphere, creating a plume in that direction. We know Earth's viewing geometry can create anti-tail spikes when we see the debris disk edge on. We know all of these features have been observed in other comets over decades. We do not know what specific parent molecules release the nickel. We do not know its exact age or precisely which star system it came from. We do not know if its unusual carbon dioxide dominance is typical of its home system or a quirk of this particular object. We do not know if we will detect similar objects soon or if interstellar comets remain rare. The anti-tail is not unprecedented. It is documented in textbooks and research papers going back 50 years. The chemical composition is unusual but not impossible. Comets form under different conditions in different stellar environments. Variation is expected. Consider the alternative hypothesis, that 3I Atlas is artificial. What would that require? First, a civilization advanced enough to build kilometer-scale spacecraft. Second, that civilization deliberately or accidentally launching it on a trajectory that brought it to our solar system. Third, that the spacecraft just happens to outgas cyanide and water and carbon dioxide at rates matching cometary activity. Fourth, that its light curve and spectral properties just happen to match natural icy bodies. Fifth, that its dust emission just happens to show size distributions matching models of comet sublimation. Sixth, that all of this occurs for the third interstellar object we have detected, after one I Oumuamua and two I Borisov, both of which also showed comet-like properties. At some point, Occam's razor cuts. The explanation requiring the fewest assumptions is that interstellar comets exist, and 3I Atlas is one. Unusual chemistry gets published in peer-reviewed journals with error bars and caveats. Speculation about artificial origins goes in blog posts and press releases. The two are not equivalent. Science is conservative by design. It requires extraordinary evidence for extraordinary claims. A sun-facing dust plume explained by known physics does not meet that bar. If Earth were to cross the comet's orbital plane at the right time in the future, we might see meteor showers from material shed during this passage. The large dust grains, the ones too heavy for radiation pressure, spread along the orbit, creating a meteoroid stream. Comet 3, Tsuchinshan Atlas in October 2024, showed exactly this, an anti-tail visible when Earth crossed its orbital plane, and calculations of potential future meteor encounters. 3. I Atlas left similar debris. 3. I Atlas is on a hyperbolic orbit. It is leaving. The debris it shed will not remain bound to the Sun. The large grains, already moving at interstellar speeds relative to the galactic frame, will escape solar gravity. They will become interstellar themselves. In a few million years, grains from 3I Atlas might encounter another star system. They might even fall onto another planet. On that planet, scientists might detect unusual isotopic ratios indicating extrasolar origin. They might speculate about where these grains came from. They might build telescopes to search for more. These ratios reflect the composition of the molecular cloud that collapsed to form the Sun, mixed with contributions from nearby supernovae and stellar winds. Another star system will have different ratios. If 3. I Atlas formed around a star that had different supernova enrichment history, its dust grains will carry those signatures. We did not get samples. We could not land on it or fly through the coma collecting particles like Stardust did with Comet Wild 2. But if 3I Atlas sheds grains and those grains eventually land on another world, someone else might analyze them. Extraterrestrial scientists studying extrasolar material. The symmetry is beautiful. 3. I Atlas will leave the solar system traveling at roughly 40 kilometers per second relative to the Sun. In galactic terms, that is slow. The Sun orbits the galaxy at 220 kilometers per second. 3. I Atlas matches that roughly. It drifts through the local standard of rest. Over millions of years, it will travel light years. Stars have typical separations of a few light years in the galactic disk. Random chance says 3I Atlas might pass within an astronomical unit of another star system within 10 million years. Probably not. Space is big, but maybe. And if it does, and if that system has planets, and if 3I Atlas is still shedding dust, some grains might get captured by a planet's gravity. They would enter the atmosphere as meteors, small flashes of light. Most would burn up. A few might survive as micrometeorites. And if someone on that planet is paying attention, those micrometeorites become scientific treasures. The grains are identified by isotopic anomalies, an unusual mineralogy inconsistent with solar system formation. Pre-solar grains, they are called, tiny, micrometers across, older than the Sun. They survive the formation of the solar system without melting or mixing. Found embedded in primitive meteorites. Comet dust from 3. I Atlas could seed another system the same way. The grains it sheds today might be analyzed by alien scientists in a few million years. They will write papers about them. They will speculate about the comet's origin. They will build models of its parent star's metallicity and age. They will get it wrong sometimes because three-dimensional trajectories traced backward through a rotating galaxy with shifting gravitational potentials are hard, but they will try. And that is what makes the story compelling. Meanwhile, 3. I Atlas itself will eventually fade. Interstellar space is cold, 2.7 Kelvin cosmic microwave background, no sunlight, no heating. The comet will freeze solid again. Sublimation stops, activity ceases. It becomes a dark iceberg drifting through the void. Maybe in a billion years it encounters another star. Maybe it gets captured into a new orbit. Maybe it gets torn apart by tidal forces during a close pass. Maybe it remains intact for 10 billion years, slowly accumulating a mantle of interstellar frost, until one day it falls into a protoplanetary disk and gets incorporated into a new comet or planet. Comets are recycled. Material flows through the galaxy in cycles. 3I Atlas is part of that cycle. A visitor from one system heading to another with a brief stopover through ours. We debated tail directions and chemical anomalies and statistical probabilities. We attached significance to every unusual feature. But from the comet's perspective, nothing unusual happened. It followed gravity. It sublimated when heated. It ejected dust and gas according to thermodynamic gradients. It obeyed Newton's laws and Kepler's laws and Maxwell's equations exactly as written. The physics worked. The comet did not care about our debates. It did not care if we called it 3I or A11PL3Z or Comet C 2025N1. It did not care if we thought it was alien technology or dirty ice. It just moved through space, shedding material, glowing in reflected sunlight, and fluorescent gas emission being a comet. And that is the real lesson. The universe does not cater to our need for mystery. Sometimes a comet is just a comet, even if it came from another star. Sometimes an anti-tail is just large particles viewed edge-on, even if the geometry looks strange. Sometimes unusual chemistry is just chemistry we are seeing for the first time because we have never had detailed spectra of an interstellar comet before. The anomalies dissolve when we apply patient observation and careful analysis. What remains is data, good data. Data that tells us about planetary formation in other stellar systems. Data that tests our models of comet activity and dust dynamics. Data that prepares us for the next interstellar visitor, and the one after that, and the dozens Rubin will find. We just needed to read the textbook more carefully. And now that we have, we are ready. Bring on the next interstellar comet. We know what questions to ask. We know which instruments to use. We know how to distinguish between genuinely new physics and perspective effects plus particle-size distributions. We know that sun-facing dust plumes come from asymmetric heating. We know that anti-tails form when Earth crosses the debris disk plane. We know that unusual chemistry reflects unusual formation conditions, not impossible origins. The textbook got longer. The next chapter has already started. And somewhere out there, between the stars, another comet is heading our way.